Okay, so there are a lot of problems that can be modeled by quadratic equations, which are known as applications. Example 9 is one example of this. So example 9 shows blood pressure and age. We're talking about blood pressure and age. And the graph in this figure illustrates that a person's blood pressure depends on his or her age. And so we have a formula that represents a formula that models a man's normal blood pressure at age A. So here we have a model that models a man's normal blood pressure at age A. We want to find the age to the nearest year of a man whose blood pressure is 125 milligrams of Hg or mercury. Okay, so we want to go ahead and look at this figure right here, the formula, and we know P equals 0.006 a squared minus 0.02 a plus 120. We want to find the age. So A represents age, so it's up here, age is A, and P is blood pressure. We want to find the age, so we're trying to figure out the age right here. Of a man whose blood pressure is 125. So we know that blood pressure is 125. We're trying to figure out the age of that man. Okay, this is a second degree equation, and A is what we're trying to figure out. We're used to seeing X, but here we're just trying to find A. And we can go ahead and set one side equals 0 by subtracting 125 on both sides. Like at 0 equals 0.006 a squared minus 0.02a minus 5. Because 120 minus 125 is minus 5. Now normally we have two options to solve this. We can't use the square root property because we have a middle term here. What we're going to do is we can either use the zero factorial or the quadratic formula. I don't think I want to factor this or even attempt to do it. So I'm going to use the quadratic formula. So A is going to equal negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And again, we're used to seeing x right here, but x is not what we're solving for. We're solving for this capital A. That's why I have the capital A there. So A is going to equal negative of the negative 0.02 plus or minus the square root of negative 0.02 squared minus 4 times A times C all over 2 times A. So I'm going to go ahead and figure out what's under the square root. So I'll go ahead and clear my calculator out. I get negative in parentheses 0.02 squared minus 4 times parentheses 0.006 times negative 5. Under the square root, I get this. Under the square root, I get this, but I'm going to go ahead and figure out this is 0.02 plus or minus square root of 0.1204 all over 2 times 0.006. I get 0.012. Now we can go ahead and give the decimal representation of this. So the square root of that is approximately the square root of 0.1204 is 0.346987. And this one is I don't round this off because I want to make sure my answer is going to be as accurate as possible. So I took it out a couple more different places than normal, and I get 0.012. Okay. What we do is I'm going to go figure out what A is. So A is going to be equal to 0.02 plus this, then divided by this. Okay. So I get 0.02 plus 0.346987, and I hit equals. Then I divide it by 0.012. I get A approximately equal to 30.58, or, and then I do 0.02 minus this, and then divided by that. Please type this along in the calculator with me so you can see what I'm doing and get the same value that I do. Okay, so I get two values. I get A equal, approximately equal to, I round it off, I use this little approximation sign, 30.58, or A is approximately negative 27.25. Now, since age cannot be negative, we're going to cross this off. Age can't be negative. So, to answer our question in a complete sentence, to go find the age of a man whose normal blood pressure is 125, the man, or the age of a man whose blood pressure is 125 milligrams, or millimeters, my mistake, millimeters. Hg is approximately to the nearest year is approximately 31 years. Okay. Now, part B, it asks you to describe differences between the normal blood pressure of men and women as they age. Well, I'm going to go ahead and write here. Looks like the men's blood pressure is higher than women's up until the age of 50, and then women's blood pressure goes up. Age of 50, it could be about 48 or so, but it looks like it's about 50, a little less than 50, so maybe about 48 there, so about the age of 48. After that, women's blood pressure is higher. Let's go to the next example. The next example goes with the Pythagorean theorem. And the sum of the squares of the length of the legs of a right triangle equal the square of the length of the hypotenuse. If the legs have the length of A and B and the hypotenuse length of C, then A squared plus B squared equals C squared. So here is a right triangle, and the legs are the two sides that make up the right angle, which are the two shorter sides. The hypotenuse is the longest side. A wheelchair ramp with the length of 122 inches has a horizontal distance of 120 inches. What is the ramp's vertical distance? Let's go ahead and look at this. A wheelchair ramp has a length of 122 inches. We look at a little ramp where the wheelchair goes up. And it has a horizontal distance of 120 inches. So from here to here, it's 120 inches. They want to know the ramp's vertical distance. We want to know the distance here. Okay. So we use the Pythagorean theorem. We know 120 squared plus x squared equals 122 squared. And a squared plus b squared equals c squared. So 120 squared is 14,400 plus x squared equals 122 squared, which is 14,884. This is a great problem to use the square root property because I have x squared and I have no x term. So I'm going to go ahead and subtract 14,400 from both sides. I get x squared equals 484. So x is equal to plus or minus square root of 484. So x is equal to plus or minus 22. And we disregard the negative because distance can't be negative. So the vertical distance is 22 inches. Okay, then part B, they're asking you to look at a requirement. Construction laws are very specific when it comes to access ramp for people with disabilities. Every vertical rise of 1 inch requires a horizontal run of 12 inches. Does this ramp satisfy the requirement? So for every 1 inch of vertical rise, you need 12 inches of horizontal run. Okay, 1 inch horizontal. We have a vertical distance of 22. We have a horizontal distance, we have a horizontal distance of 120. Excuse me. Okay, I mixed up excuse me. This should be every 1 inch vertical rise. A 1 inch vertical requires a horizontal run of 12 inches. I had that mixed up, sorry. Okay, so now we have a vertical distance of 22 inches. So we have 22 inches. We're trying to figure out what we need for horizontal run. So if I do a proportion here, I have 1x equals 22 times 12. I get 264. So I need 264 inches of horizontal run for every 22 inches of vertical distance. And I only have 120, so no, it does not. Okay, we're getting to the end of this section, so I'll go ahead and stop the video. And section 1.5 is super important in this chapter. We actually in this course, we solve a lot of quadratic equations between now and the end of the semester. So it's important to know how to do the zero factor rule, the square root property, the special case in the square root property. We see that a lot when we get to chapter 3, and then also the quadratic formula. Okay, so let me know if you have any questions.